Okay. Yeah, so it has started. So this is going to be 11th. This is diffusion model 3. Okay. So right. So now what we are going to see is another interesting thing. I mean, this is a very short thing, but nonetheless, it deserves a separate discussion on its own. So this is number 11, which is again diffusion models. Models. It's the third part. Okay. Let's so okay, right. So let me write down the objective that we just derived, right? Particularly, we derived this objective function that that we are seeing here, right? So what is the objective? I will write it down. So this is 1 by sorry. So this is 1 by 2 sigma q of t square alpha t minus 1 bar into 1 minus alpha t whole square divide alpha t whole square over 1 minus alpha t bar into norm of x theta hat of x t comma t minus x naught whole norm whole square. Right? This is what our class function is, right? I have just written this thing down, this thing. Okay. In that case, uh, so basically I want to basically do something so that my alphas are also learnable, for example, okay? I want that is the goal, let's say. Okay, that is what we want to see. But I mean, note that it's not trivial. So for example, so a naive way is to basically say that my alphas are going to parameterize by some network eta, and I am going to make them time dependent, okay? Because alphas are dependent on time. So I have parameterized it using a neural network eta, and it is taking t as input basically. However, note that the problem this will be this is a very difficult parameterization. This is a very bad design choice, so to say. Why is it a bad choice, bad design choice? Because this it is not just alphas that you have to worry about. You have to also worry about this alpha t's also, right? So these alpha bars as well. I mean, in that case, what will be your alpha, let's say alpha bar eta of t? This is equal to product of alpha eta of t equal to 1 to t. This is what it is going to be. Now, see that this is a sort of a bad choice because you have to take, so you will have to, if you want to calculate alpha bars because you want to calculate this thing, uh, you will have to basically go through all the time steps, pass, so you will have to do t, the small t passes through your network alpha eta. So you'll have to pass t equal to 1, t equal to 2 until t equal to small t, get all these alphas and multiply it, and then you will get this thing, right? I mean, this is a sort of a bad design choice. Like if you just parameterize alphas like this, your alpha bars are going to give you trouble. You can do some sort of caching. I mean, you can save them in memory, something like that. But there are more elegant ways to do it. That we'll see how to do it. But is it clear why is this a bad design choice?
Yes, yes.
So so let's look at it. So this thing, right? Let us probe this thing. So well, first of all, what is sigma q? Sigma q of t, right? Sigma q of t. What is this thing? We saw what this thing was. Uh, where is it? Yeah, this is the thing, right? This sigma q. So this is equal to 1 minus alpha t, right? 1 minus alpha t minus 1 bar divided by 1 minus alpha t bar. This is what it is, right? Yeah. So let's first substitute this sigma q in this objective, right? To simplify it, this thing is equal to 1 over 2, 1 minus alpha t square, 1 minus alpha t minus 1 bar square, 1 minus alpha t bar square. So I have just squared this and inverted it into into alpha t minus 1 bar into 1 minus alpha t square divided by 1 minus alpha t bar. This is what it is. Okay, can something cancel out? Oh wait, I think I have written something wrong. Uh, wait. Yeah. In the numerator, oh, this is alpha t. Okay, okay. It's up. Everything is fine. Sorry, I got it. I myself got confused. So what is going to get cancelled? So this square will get cancelled with this term. This square will get cancelled. So wait, is this entire thing getting cancelled? Oh wait. I think I made a mistake. This was already sigma q square. Right? So okay. Yeah. So this thing, it's so this th oh yeah. So this thing is itself was sigma q square, right? I missed that point. Uh, so if that is the case, so this is actually sigma q square, and because of that, uh, what is it? So there will be no squares involved basically. So there won't be any squares here. Sorry for this mistake. Okay. Apologies. Uh, so there won't be any squares involved, and this is what it will be. Now let's see what is getting cancelled. This thing gets cancelled, right? Uh, what else? So this thing will get cancelled with this square will get cancelled, and what will remain inside is as it is, right? So that is norm of x theta hat minus x naught norm whole square. Is this fine?
Yes, yes.
Yeah. Sorry for that mistake. Okay, so uh right. Uh I think I'm doing something wrong. Should this be 1 minus alpha t bar whole square? Is this whole square? Just let me see. I think that is whole square. Oh right, this is whole square. I'm getting confused. This is whole square. This is so okay. Okay, just a second. Uh, 1 minus alpha t bar. This is 1 minus alpha t bar whole square, and only one thing will get cancelled. The square will get cancelled. This is fine. This is okay. Sorry. So I mean, I just got confused between the sigma q's and this term. So sorry for that. But now it's correct. Okay. So what is this thing? Just write. I will just write it down afresh so that there is no confusion. So there is 1 by 2. There is alpha t minus 1 bar into 1 minus alpha t divided by 1 minus alpha t minus 1 bar into 1 minus alpha t bar. Okay. Norm of x theta hat of x t comma t minus x naught norm square. Okay. This is what it is finally. Sorry. Okay.
Uh, so what is the
Yeah.
argument of this? I mean, x cap theta x t comma. In the last equation, you wrote something x t comma.
So this is xt comma t. Sorry. So so it is taking xt and t as input. That's all.
Yes, yes.
Okay, but this is not of our interest right now. So I mean, we will just keep writing this thing down, but it is not of our interest because we want to see what if we want to learn these alphas. So alphas are all outside, so we need not worry about what is here because this is only considering theta. This is only considered for theta, right? We
Yes,
are
yes.
worried about alphas now. Okay,
Yeah.
if this is the case, let's try to do some manipulations, right? Let's try to do some manipulations. Before going there, let's do some simple things. So I will again use a trick that we did a while back. What is it? So this thing is equal to alpha t minus 1 bar minus alpha t into alpha t minus 1 bar. So what will this thing become? So this is alpha t minus 1 bar. Alpha t minus 1 bar is product. So this thing is again product of alpha t's t. Sorry, this is product of alpha i's I going from 1 to t minus 1, right? And you're multiplying it with alpha t. So this thing will become alpha t bar. Is this, I think we did something similar yesterday as well.
Yes,
Is it
yes.
fine?
Yes, yes.
Yeah.
I remember. Yeah.
So, yes. So if that is the case, then what will this thing become? So this will become 1 by 2 alpha t minus 1 bar minus alpha t bar divided by 1 minus alpha t minus 1 bar to 1 minus alpha t bar. So I'm again now going to do some, so I will, for brevity, I will just write it as x theta hat, but there is always this argument xt comma t minus x naught whole square. Okay. Now I'm going to do some modifications and simplifications, but I thought this is important. That is why I'm doing it because otherwise I think it's a good exercise to do it. So I'm just doing it. So this is alpha t minus 1 bar minus. So what I'm going to do is I'm going to add and subtract something. I'm going to add and subtract alpha t minus 1 bar and alpha t bar. I'm going to subtract it and then I'm going to add the same thing. 1 bar alpha t bar. And there is always this alpha t bar that is already there. This thing divided by 1 minus alpha t minus 1 bar into 1 minus alpha t bar. There is this norm square. Okay, I'm just writing it as norm square, but I hope you understand what I'm referring to. This thing is half. Now take alpha t minus 1 bar in common. So this will become 1 minus alpha t bar plus take alpha t bar common. This will become, okay, maybe add a minus sign here. Add a minus sign. So this will become 1 minus alpha t minus 1 bar divided by 1 minus alpha t minus 1 bar 1 minus alpha t bar. Okay. So, I mean, what I'm doing right now is very similar to something called partial fractions, where we try to decompose a given fraction into two fractions. That is what I'm doing. This is half and okay. Now, take, so I will split this term in two terms. Now, this will become alpha t minus 1 bar 1 minus alpha t bar divided by 1 minus alpha t minus 1 bar into 1 minus alpha t bar minus alpha t bar into 1 minus alpha t minus 1 bar divided by 1 minus alpha t minus 1 bar into 1 minus alpha t bar norm whole square. Okay. Now, okay. Now, what is getting cancelled out? This thing will get cancelled out here. This thing will get cancelled out here. Okay. So, what are we left with? This thing is half. So this first term is alpha t minus 1 bar divided by 1 minus alpha t minus 1 bar minus alpha t bar over 1 minus alpha t bar norm of x theta hat minus x naught whole square. This is what it is. So I did some simplifications. You can ignore it if you want, but this is the final thing that we come up with. So note that these two terms have similar form. Like This is at time t minus 1 and this is at time t. That's all, right? So it
Yes,
is
yes.
like, so now this is what is important, and this is what we are going to see that this is something interesting. Particularly, these terms are interesting. Okay, now just I will take a detour and just keep this thing in mind that this is what our objective function finally looks like. Okay, let's remember what this thing is. Q of xt given x naught. What was this? This thing was a Gaussian distribution, right? Xt. Uh, It was the mean was square root of alpha t bar x naught, and the mean was and the variance was 1 minus alpha t bar I, right? This is something that we did last time as well. Okay. Uh, in this case, we can define signal to noise ratio. Signal to noise ratio. If you are from electrical engineering background or signal processing background, you know this is SNR. So SNR for a Gaussian distribution, it is defined as mu square by sigma square, right? So it's like the mean is your mean so it's like you have a Gaussian distribution. The mean is your main signal, right? That is your clean signal. So that is your signal square divided by the noise is coming through the variance because of the variance, that is sigma square. So your SNR is defined as mu square by sigma square. Okay. So for if for this distribution, right? For this distribution, for this distribution, what is your SNR for this distribution? SNR at time t, what is this? So the mean is this thing, right? I mean, uh, uh, wait a second, just a second. Mm, uh, 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 so your mean, uh, so your mean coefficient rather is, so this is alpha t bar divided by your sigma square, which is this thing, is 1 minus alpha t bar. Okay. And this is exactly what this thing is. This thing, this function. Is it fine?
So actually, I could understand this SNR is equal to mu square by sigma square, but how did you reach to this expression, say alpha t bar and then one minus? Because I mean, this second term. So how is this equal to mu square by sigma square?
Okay. So okay. So for this distribution, right? This distribution, this is the mean and this is the variance. This is the sigma square, isn't it?
Yes, yes.
And in this case, so this is I mean, it's like you want to get the ratio of the signal to the noise, right? I mean, uh,
So if I
like
take the square, is if I take the square of the second term in this distribution, this becomes alpha t bar, and divided by the, I need to take the square of it. So 1 minus alpha t bar ka whole square.
no, so this is already sigma square, no?
Oh,
So
I see. Yes, now I understood.
yeah,
Yeah, clear, clear, fine.
yeah, right. So this is already sigma square, and this is your mean. So this square is alpha t bar, and this is already squared, so this is 1 minus alpha t bar. Is it fine?
Yes, yes.
Okay. Now, so now can you see that this thing is exactly same to this, similar to this thing? Can you see that? Alpha t
Ye-
bar over 1 minus alpha t bar.
Yes, yes.
So our objective, whatever our objective was, so maybe let me write it as L. L is actually what? This is half 1 by 2 times SNR, SNR at time t minus 1, right? This is at t minus 1. SNR at time t minus 1 minus SNR at time t into norm of x theta hat minus x naught norm whole square. Is it fine?
Yes, yes.
Okay. Now let us think about it, right? So SNR, so okay, as we go, so in our forward process, so we have a forward process, right? Which which starts from some x naught and it eventually becomes totally corrupt and becomes a complete noise xt. So as we go forward, right? As we move forward, what should be the SNR? Should the SNR decrease or should the SNR increase? Since, I mean, if we think about it like very intuitively, right, that at the end there is no signal left, right, because it's complete noise. Initially, the data is little corrupted, but still the signal is there. But at the end, there is no signal. So SNR is actually decreasing here, right? So
Yes, SN,
at time t minus one, the SNR has to be greater than at SNR at time t, right?
yes, because in the forward process, I mean, since we are increasing the noise, so increasing
Yeah,
the value of the variance. And if we are
yeah.
increasing the value of the variance, then SNR
Mm.
decreases. Right, right. Yes,
Yeah. Right.
yes.
So SNR, so this thing is actually positive. This quantity is actually positive, right? This is not a negative quantity. That's the first thing. Now,
Yes.
this is quite nice, right? Instead of, so remember, if you want to actually learn the parameters, we saw that this is a bad choice because if you go on parameterizing each of the alphas, this is a bad choice. I mean, your alpha bars are going to give you trouble. However, if you parameterize the SNR directly, that is something which is good, right? Because in your loss function, you can directly, uh, like there is one neural network which is modeling your SNR. You can calculate it for two time steps instead of all the time steps. Take the difference and you are done, isn't it? So this is a smart, rather a smart parameterization. So to make the parameters learnable, what you do is you make your SNR at time t. You make this thing. So again, so SNR is a positive quantity always, okay, because it is signal to noise ratio. It cannot be negative. So what you do is you take exponential because exponential can never be negative, okay? Exponential of minus. So you take this parameterization instead. So this is your new parameterization. I mean, so okay. So this is your neural network. This is your neural network, right? Eta is your parameter. Omega eta is your neural network. It takes t as input, and you make sure that omega eta is like, so okay, what do we want? We want that SNR of t as a function of time, right? Should always decrease, right? SNR should always decrease. It should go like this, right? If you take this and it should always be greater than zero. That's another thing. So exponential takes care of the fact that this thing is always greater than zero. But to make sure that this thing decreases with time, right? You need, so when will the exponential decrease with time? When the argument inside is decreasing. So it is negative, so this thing should increase. So this omega eta of t, this is a this should be modeled as a monotonically increasing neural networks. Increasing neural network with parameter eta. So, so if your omega eta is increasing, right? Minus of omega eta is decreasing, and exponential of a decreasing thing is also decreasing, right? So this is how you can like parameterize your parameters. However, here you haven't parameterized your So here you haven't made alphas to be learnable. Instead, you have made your SNR to be learnable. But what is the relation between SNR and your parameters alpha? Well, this is the relation, right? I mean, this is what the relation was where we started from, right? So what you can do is you can do a simple substitution. So SNR of t, you are modeling it as exponential of minus omega eta of t. But you also know that this is equal to alpha t bar over 1 minus alpha t bar, right? So this is also equal to alpha t bar over 1 minus alpha t bar. So from here, what you can do, you can simply calculate what is the value of alpha t bar, right? So this is exponential of minus omega eta of t is equal to, if you take this here, so this will be exponential minus exponential into alpha bar. You take the alpha bar into the RHS, so it will become alpha t bar into 1 plus exponential of minus omega eta of t, right? This is what it will become. And this means that alpha t bars is equal to exponential of minus omega eta of t over 1 plus exponential of minus omega eta of t. This is something that is quite well known. This is also known as sigmoid
Yes,
of sigmoid of minus omega eta of t, right? And this also implies that 1 minus alpha t bar is nothing but sigmoid. So this is minus. I mean, if you do some calculation, you will. It is simple to show that 1 minus alpha t bar is sigmoid of just omega eta of t. That's all. So, so I mean, this. So please note that we didn't start from here. I mean, this is something that you could not come up with directly. What we did instead is we started with parameterizing the SNR. We parameterized the SNR and it led us to this particular parameterization. And this is what is helpful. If we know, if we had started with this thing, we could have directly written whatever we have derived to. But yeah, nonetheless, this is helpful, right? I mean, this is how. So now what you can do is you can, this SNR will be, these two will become function of eta. This is a function of theta. If you want to learn eta, you can take the gradient with respect to eta, right? If you want to learn theta, you can take respect to theta here. And you can optimize both eta as well as theta. There's no issue. Is that fine?
yes. So, do I need two neural networks to learn two different parameters, or would I
No,
be
no,
using a single neural network to learn both the
no. So,
parameters?
so this is a single neural network, right? So there are two neural networks. One is eta for the parameters, and there is another theta for the denoising. Okay, but remember that this, so eta is shared across time. So for any time you are using the same parameter eta.
Uh, okay. So, I mean, I would be using one neural network to train to get the, I mean, to get the, to optimize this WN term while keeping the value of the theta constant. And then I would
Yeah,
be using another neural network to optimize the value of the theta by keeping what? Which value constant? Uh,
this thing constant, everything else constant. So the SNR thing will remain constant while you're optimizing with respect to theta. This will remain constant while optimizing with respect to eta.
oh, I see.
Yeah.
Okay.
I mean, you can just think about it, right? So if you take the gradient with respect to eta here, this thing is the only thing that depends on eta, right? This thing will come out here out of the gradient. And when you take the gradient with respect to theta, this thing will come out and this thing will be inside the gradient.
Yes. Yeah, fine.
So yeah, so that is how you can learn. So this is another like sort of an insight into the diffusion models, that you can look at the parameters in terms of SNR. This is the crucial point, that you can also think about these alphas as SNR. I mean, we did have some intuition about it when you discussed this thing, right? That initially we want alpha i's to be such that it is just a Dirac delta at x naught, and at the end we want it to be Gaussian 0, 1. I mean, we didn't talk about SNR explicitly there, but we sort of got a we sort of deduced introduced an idea of how should the alpha is look like, what should be the function to schedule this. But this is another way to look at alphas, that alphas are actually something that is governing your SNR, and you want your SNR to decrease, and you can learn it using this kind of for modeling, this kind of parameterization, so on and so forth. Yeah. So yeah, so this is it. Yeah. Think we can stop this part here itself. Okay. So I'll just stop the recording here unless there are any questions.
No, this is clear. And what would you be covering in the next lecture?
Actually, so I'm planning to take like another half an hour now itself,
Okay,
because
okay,
I will be a little busy next week. So I'm just so there is this last thing that is remaining, which I will just cover in like half an hour or something, and
okay,
yeah, then I will just stop. Yeah,
okay, okay. So can we take a 5 minutes break if it is okay with you?
yeah, sure, sure, uh,
Okay, yeah,
totally fine.
thanks.
Let's take a 5 minutes break. I'll just stop the recording. Yeah.
Okay, fine, thanks.